Hello and welcome to this physics class presented to you by O3 Schools JAMB app. O3 Schools app is, well, as the name implies, an application which you can install on your Android phones and your Windows laptops, and it helps you as you prepare for JAMB. And you may ask, how does it help you? Well, minus all the information which it gives you, which is plentiful because it actually has a place where you can actually check for what schools have what courses. There's a section where you can check for what subjects are required for different courses. Then there's also the mock exam feature wherein you can pretend you're actually on your in your center the day of your jam, write your exam so that you can gauge not just your knowledge but also your speed. And obviously, there's my personal favorite, the question search feature, in which you can search for a question like by topic. You can simply search for the topic, and all the questions which JAMB has set in that topic will come out, and then you can answer that as you read each topic to gauge your level of, understanding for that topic. And all these and more are available to you once you install the app and activate. Yes, not just install, you also have to activate this application. And the activation fee is simply 2,500 naira only. That's cheaper than, well, even your physical past questions. Just getting this app gives you access to all the questions in all your subjects, not one, not two, all of them. So activating your app costs 2,500 naira only. And there are several ways of activating this app. Once you just open the app, the different payment modes will be available to you. Choose the one that works best for you and activate your application. Once you do this, you shall be able to gain full access to all these features which I've described and even more. And you can get your 3 schools jam app and be on your way to getting a very good score in your examination. So remember, get your 3 schools app, activate it, and you are one step towards success. And with that, let's come to this physics class. And in this class, we shall be looking at sound waves. Sound waves. Well, as you know from our when we looked at waves, sound is a mechanical wave, and also it is a longitudinal wave. So, what is sound wave? Well, sound wave is a wave to be created by vibration of objects. Once objects vibrate, they create sound. Even when a human is talking, they are simply vibrating the molecules of air to produce sound, which the person can then hear. And sound wave, like we said, is a mechanical wave, which means it requires material medium. So sound cannot travel if there's no material medium. So sound cannot travel in space, it needs medium to travel through. And while traveling, it travels faster in denser materials than in less dense, implying that the speed of sound is greatest in solids, then liquids, and then finally gases. So the speed of sound in normal air at your standard temperature is about 340 meters per seconds. And yes, I said standard temperature because the speed of sound also varies with temperature. Well, quite simply, this can be given by V2 over V1 equals the square root of T2 over T1, where V equals to the velocity of sound and T equals to temperature. And please note that this temperature must be in Kelvin. So if you are given a question where you have to study the variation or the velocity of sound with temperature, then that is your formula. So the higher the temperature, the faster the sound, and the denser the material, the faster the sound. So that is that. Now, sound undergoes the properties of all waves except for polarization. And we know why it doesn't undergo polarization. Polarization exists only for transverse waves, but sound is longitudinal, therefore no polarization. But it undergoes every other process. Now, when sound is reflected, it has a special name, which I believe we should know already, which is echo. When sound is reflected, we generally call it an echo. An echo is simply the bouncing back of sound wave after hitting a plane obstacle in its path. Now, actually, echo has a lot of uses actually. Echo is used in sonar, basically in detecting submarines underwater. Echo can also be used in exploration for gases and natural resources. How? They send the sound wave down into the ground, and by analyzing the type of sound they receive back, the different levels of the sound, they will know what material should be able to produce sound of that level. And the one you generally solve on most in this topic is for calculating the depth of the ocean or distance to an object. What do I mean? If you generate a sound from a source here, and this sound travels to meet this object here over a distance d, now before you hear the echo, it means the sound goes and comes back d and d. So if you know the velocity of the sound and you know the time it took to go and come, then obviously you can solve your distance, because speed or velocity will be equals to distance, but rather than just 1d, it's going and coming. That will be 2d over t. And this is simple calculation when dealing with echoes. Now remember, the reflecting surface for this sound doesn't have to be straight. When dealing with submarines, they are sending the sound down into the ocean, and the ocean depth reflects the sound back, but it is still the same idea. Even if they call it h or any other thing, it's still two distances over the time. Okay, so now that is echo. Now, when looking at sound, what are the characteristics of sound that we have to look at? When we hear sound, what things come to mind? Well, there are three things that define sound. There is pitch, there is loudness or intensity, and then there is quality or tone. So we're starting with pitch. Pitch is simply the position of a note on the musical scale. It's that simple. And this pitch depends on frequency. Pitch depends purely on the frequency of the sound. The higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. If you play piano, then you know that playing your keyboard from the different sides, maybe getting the same notes, but they are different pitches. One is higher and one can be lower. Now, when analyzing for pitch, they use either a toothed wheel or a cardboard box with holes within them. So either something like this, this is a circle with teeth, and then you can have something hitting it as it rotates, or they use still a circle, but it now has holes within it. Now, no matter which of them they are using, to calculate the frequency of this sound, becomes that frequency equals to number of revolutions, let's call it revs, number of revolutions times. If they are dealing with teeth, they then say times number of teeth. Or if they are dealing with this one with holes, then they say number of holes all over the time taken. So either way, you get your frequency. Toothed wheel, number of revolutions times number of teeth by time taken. While for your discrete holes, number of revolutions times number of holes over the time taken. That's pitch. Next, loudness or intensity. Loudness is the magnitude of sound reaching the ear, basically. The magnitude of sound which you hear. That is the loudness. And the intensity is simply, well, yeah, the ability of that sound, the amount of sound that is reaching that particular location. Loudness depends on the intensity which also depends on the amplitude. So, how to look at intensity? Intensity at any point follows the inverse square law. That means the maximum intensity divided by distance squared from the source of the sound. So the farther your intensity, or rather the farther you go from your source, the lower the intensity of that sound. Okay, the last but not least, quality, quality, quality. Quality is simply the characteristic of any musical note which enables you to differentiate one instrument from another. That simply implies that two different instruments could play sound of the same frequency and at the same loudness, but they will not sound exactly the same. And what factors into that difference is what now referred to as the quality of that sound. I could get the idea. So one more time. Pitch is the position of the sound on the musical scale. Loudness is the magnitude of the sound between the observer, while quality is simply the special characteristic unique to each sound that differentiates one instrument from another. And your quality depends on the overtones. The overtones or harmonics. When we study them, we realize that they are closely related. So the quality depends on the overtones or the harmonics of this sound. And now these are the characteristics of your sound wave. Now, your sound can be produced with different instruments, but we are going to study just a few of them. First of all, you should know that, yes, in this topic, we kind of look at music a lot. Your musical instruments are of various types. They are the percussion instruments, such as your drums, which you are hitting. They are the wind instruments, such as your trumpets, which you blow into. Then there are the stringed instruments, such as your guitar. So that's the three types of instruments we look at here. Your string, your wind, and your percussion. But when it comes to our solving, I'll try to look at just two of them, the string and the wind. We still call them string and wind anymore. We call them you can call the first one string, but for the second one, we then call it pipe. The wind is passing through a channel, and that channel is the pipe. And in the pipe, there are two. We have the open pipe and the closed pipe. Now, please don't let the fact that they called one closed confuse you. Your open pipe is open at both ends, while the closed pipe is simply closed at one end, not both ends. So do not think your closed pipe is this. If it was this, then there's no way to get the sound into it. Instead, it is open at one end and closed at one end, while your open pipe is open at both ends. Then your string, well, is simply something like this. Now, for each of these, there exists several harmonics and several overtones. However, how do we get to the harmonics or to these overtones? We can only get to these harmonics and overtones when we first of all identify what is known as the fundamental frequency. Now, fundamental frequency is presented by F notes. That simply implies that every instrument at its base, at its lowest frequency it can produce for sound, that is your fundamental frequency. Then harmonics simply imply that we are stepping up this frequency and increasing it in regular intervals. So we're not just adding two or three, no. Harmonics are multiples. So, first of all, before we analyze any instrument, first of all, note the fundamental frequency, and then and only then can we look at the harmonics and the overtones. So, let us start off with our string. Okay, so we shall be starting with our string. Now, when looking at the wave on the string, we have to start from what is known as a fundamental frequency. Now, fundamental frequency is the lowest frequency you can get, the basic place you are starting from. And please note, your fundamental frequency is the same thing as the first harmonic and is the same as the zero overtone. That's F naught. After this, there's another level to the frequency, which is your F1, and that is known as your second harmonic or your first overtone. Then there's yet another level, F2, which is your third harmonic or your second overtone. So you'll notice that these numbers, the subscripts to your F, follow your overtone, not your harmonic. Do not make that mistake and mix them up. So the number following your frequency are derived from the overtones. The fundamental frequency is F naught because it's zero overtone. Your first overtone is F1, second overtone F2. That means your nth overtone will be Fn. Okay, that is general, by the way, for both pipes and strings. So once we look at that, this is established. Now let's analyze the different harmonics and overtones for your string. Now fundamentally, the basic way you can pluck your string is in this easy manner from the center to create oscillations. Now, this is the length of your string, L, but you've created a wave in this string. How many wavelengths are there in this wave? If you remember your analysis for waves, the distance from here to here is one wavelength, another wavelength, and so on and so forth. But if I look there, I'm simply having what appears to be just this top on it, top and bottom, like one circle, but not a cycle. In that case, this is simply half of this one, is half a wavelength. That means that this my length equals to half wavelength or wavelength over 2. And as such, the wavelength must be equals to 2L. Once I've established this, the next thing I must then know is that V is F lambda naturally, and F becomes V over lambda. Therefore, the frequency for this stage, our F naught, our zero overtone, or fundamental frequency, therefore becomes V over, instead of lambda, lambda is 2L. V over 2L. That is our fundamental frequency. See, very easy. Now, what about the next stage? The next stage becomes, which is my first overtone or my second harmonic. What if I pluck the string from 2 points at once? In that case, pardon the diagram. In that case, I should be getting something like this, because I'm plucking from 2 points. And as such, this is what I get. Again, this is my length. And now, how many wavelengths do I have? It's a complete cycle. And as such, that is one full wavelength. Therefore, if I use my normal formula for frequency, or now I know I'm dealing with F1, the next level, that becomes V over lambda. Lambda is L. So F1 equals to V over L. Now, I could stop here and just tell you, or I'd like to actually show us how we notice this. Let's try for the second harmonic, or rather, the third harmonic, or the second overtone. In that case, we are going to pluck it at 3 points at the time. So something like this. Now you notice half a wavelength, half another wavelength, half another wavelength. That's 3 over 2 wavelengths, 1.5 wavelengths. So L equals 3 over 2 wavelengths. And if I cross multiply, wavelength must be 2L over 3. Therefore, if I decide to find my frequency in this case, F2 then becomes V over wavelength is 2L over 3. That becomes V times 3 over 2L, which is 3V over 2L. So if you look at this, we can notice a particular trend. Let's take it here. F0 is V over 2L. F1 is V over L. F2 is 2V over L. F3 is going to be, sorry, this is 3V over 2L. F2 is 3V over 2L. F3 is going to be 2V over L. F4 is going to be 5V over 2L. Now, some of us may say the number is changing and coming and changing. No, actually, the number is increasing uniformly. This was 1V over 2L. This is 2V over 2L, but 2 cancels 2. This is 3V over 2L. This should be 4V over 2L, but 2 left us with just 2 at the numerator. This is 5V over 2L. Actually means that my number is being multiplied by an increasing number. That means F1 is being multiplied by 2, F2 is being multiplied by 3. And as such, I know that Fn must be multiplied by n plus 1. So this becomes Fn equals to n plus 1 V over 2L. And we know that V over 2L equals to F0. Now, as a result, this is what I need you to memorize. You don't have to memorize for each of them. You need to memorize the fundamental frequency and the general formula. As well, you need to keep an idea of the diagrams in your head, because at times they could simply ask you purely for the wavelength and not even for the frequency. If this is the length and this is the harmonic or the overtone, what is the frequency? Okay, so these are the type of things you can do with strings. Now, before we move on, there's one more thing you should know about strings, and that is with an experiment known as the sonometer. With a sonometer, they're able to analyze what the frequency of this wave should be purely because of the properties of the string producing the wave. So the sonometer, what they know about it is that the frequency is inversely proportional to the length. This frequency is proportional to the tension, and there's inverse proportional, and not just tension, the square root of the tension, and it's also inverse proportional to the square root of the mass per unit length. Now, please note, this is capital M, not small m. This capital M here refers to mass per unit length in kilogram per meter, not just kilogram. So please do not mix up the two. And when all these are combined and the variation is removed by introducing the constant, it is found that F0 equals 1 over 2L square root of T over M. So with a sonometer, this is the formula relating frequency to either tension, length, or mass per unit length. Now, at times, though, they don't give us mass per unit length, and they give us just normal mass. I could either use my normal mass to divide my length and therefore get the mass per unit length, or I could also say 1 over 2L square root of TL over normal mass, small m. So this is everything you need to know about the behavior of a sonometer. If you have been asked to find how one property varies with another, keep all the others constant, generate a quick formula for that one, and you can be on your merry way. And now that is what we need to know about strings. Now let's start off with our pipes, with the open pipe first of all. Now, with our open pipe, something like this, our first harmonic or fundamental frequency looks like this. This is our fundamental frequency. Now you may be like, how many wavelengths are here? This is a quarter of a wavelength, and another quarter, because if you look here, from here to this is a full wavelength, this is half, and from here to here must be a quarter. So quarter wavelength, another quarter wavelength, which means that L equals to lambda over 2. Quarter plus quarter gives half, and that lambda equals to L. Therefore, F naught must be V over 2L. And this looks quite familiar. Yes, because this is the same formula which we generated for our strings. And consequently, you must now know that your string and your open pipe take exactly the same formula, no differences whatsoever. That means in this your open pipe, F1 will also be 2F notes, F2 will be 3F notes, and consequentially Fn will be n plus 1 F notes as well. That means formula wise, your open pipe and your strings are perfectly identical. What's the difference? In your string has nodes at the end, regions of no movement. Your string has nodes at both ends. Your open pipe has antinodes at both ends, regions of maximum movement, while your closed pipe, which is the next thing you have to look at, actually has antinode at the open end and node at the closed ends. Keep this in mind, you can be asked. One more time. The string has nodes at the fixed ends. Your antinodes, or rather, your open pipe has antinodes at both ends, while your closed pipe has nodes at the closed side and antinodes at the open side of the pipe. Now let's analyze this closed pipe properly. Analyzing purely now for our closed pipe. Remember, our closed pipe is not closed at both ends, but purely on one end. So, for a closed pipe, we have something like this, and my fundamental frequency is this. That's all. What does that remind me of? That is simply like this part only, which is a quarter of a wavelength, not up to a wavelength. That means my full length is giving me a quarter wavelength, and that lambda must be 4L. Therefore, F naught being V over lambda becomes V over 4L. That is the fundamental frequency for a closed pipe. Now, what about the first overtone? The first overtone or the second harmonic of this closed pipe? In that situation, remember, the open end must carry antinodes, and therefore, if this is the fundamental, it simply does this. See, we still have antinodes at this end. But you notice it's pretty much added a full cycle so that it could still come out with antinodes. That means we're adding a full wavelength to a quarter wavelength. That's 5 over 4 wavelengths. So my length becomes 5 over 4 lambda. And therefore lambda must be 4L over 5. Therefore, F1 will be V divided by 4L over 5, which is V times 5 over 4L, which is 5V over 4L. So this is the formula for the first overtone of a wave in a closed pipe. What if we look at the second overtone so that we can also see how this one trends before generating the general formula? This fundamental, first overtone, second overtone. So this is my length. How many wavelengths are here? This is one wavelength, two wavelengths, and still that quarter we started with. So that is 2 1/4 wavelengths, which is L equals to 9 over 4 lambda. So lambda equals to 4L over 9. So F2 becomes V divided by 4L over 9, which is V times 9 over 4L is V equals to 9V over 4. Sorry, which is F equals to, 9V over 4L. This is F2. Okay. Oh God, I'm getting tired. Thank God, though. I've made another blunder. But this, nope, I've made another blunder. But hunger did do me. But this blunder is not hunger. I started this. This blunder is not too far. It's just here. But if you finish, you can take the rest after. Okay. What did they do me this afternoon? Okay, so let's look at the first overtone. Now, in the first overtone, we're going to still have this fundamental, but then remember we have to have antinodes at the open part. So it's not going to come here and stop, rather it's going to continue until an antinode is formed. In this situation, ask yourself, how many wavelengths are here? This is half a wavelength and then a quarter. That means my length equals to 3/4, 3V over 3 over 4 rather wavelengths. And therefore the wavelength must be 4L over 3. So this my first overtone becomes V divided by 4L over 3, which as we are aware is the same thing as saying V times 3 over 4L. Therefore F1 must be 3V over 4L. Now I would have stopped there, but let's just look at one more step so we can see how the trend occurs within a closed pipe. Now what it does is, again, fundamental, first overtone, second overtone, ensuring that we have antinodes at the open end. Now let's see. From year to year is actually a cycle, which is a wavelength, plus a quarter wavelength here. That is 1 plus a quarter. Therefore, my length in this case is 5 over 4 lambda. And that lambda must become 4L over 5. So, F2 becomes V divided by 4L over 5. V times 5 over 4L, which is 5V over 4L. That's my F2. So if I look at this now, do I notice the trend? I should. It is increasing by only odd numbers, while my denominator maintains a constant over 4L. As such, F0 equals to V over 4L, F1 equals 3V over 4L, F2 equals 5V over 4L, F3 must then be 7V over 4L. How do we get this number? You can simply say 2 times 0, 0, plus 1, 1. 2 times 1, 2, plus 1, 3. 2 times 2, 4, plus 1, 5. And therefore, Fn must be 2n plus 1 V over 4L. And because no V over 4L is F0, then Fn must be 2n plus 1 F0. So just like for your open pipe and your strings, what you're trying to memorize is fundamental frequency, the general formula, and then the structure of the wave within the pipes. So to find for any overtone at all, where n in this case, as in all the other cases, n here is a number of overtones. Okay, So all you simply have to do from here is apply this knowledge, which you shall do right now as we open our O3 Schools JAMB app to solve questions. Our first question comes from the year 1994. 1994, that's very old. 1994, question 24. The question says, the notes produced by a stretched string. So now we know already we are dealing with a string, has a fundamental frequency of 400 hertz. Okay. If the length of the string is doubled, I mean, this is fundamental frequency 1. Then if the length of the string is doubled, that means L2 equals to double of the initial length, while the tension in the string is increased by a factor of 4. Tension 2 equals to a factor of 4. 4 times TO. We have to now find the new frequency. Okay. Now, how do we solve? All we have to remember is, in a string, since we are given tension and length, I know I should be dealing with this formula. F naught equals to 1 over 2L square root of T over M. Now we notice they did not give me mass. That means my mass is not varying, and I could pretty much, almost ignore my mass in my calculations. But what would the easiest way to solve it be? I could use a ratio, right? I could say if this is F naught 1, say this is F naught 1, then over F naught 2 equals to 1 over 2 L2 square root of T2 over M. Now I already know M will cancel M because there are no values for that. And if I put in my values, F naught 1 becomes 400 over F naught 2, which I do not know, equals, here becomes 1 over 2L1 times square root of T1. 1 times square root of T1 is simply going to be square root of T1. I leave that like that. This over becomes divide. What do I have here? 1 times square root of T2. Square root of T2 over 2L2. So, one more time, 400 over F naught 2 equals to root T1 divided by 2L1 times 2L2 divided by root T2. You see, this is what I have. However, I have relationships. I know that, this is T1, sorry. I know that 400 over F naught 2 should be root T1 over 2L1 times 2. Now, instead of L2, I know that L2 is 2L1. So this becomes 2 times 2L1. And I know that T2 is 41. Root 41. So 400 over F naught 2 equals to root T1 over 2L1 times 2 times 2 is 4L1 over square root of 4 is 2 root T1. So can I cancel out? Yes. Root T1 cancels root T1. L1 cancels L1. 2 times 2 is 4, and that cancels 4, which means everything here is 1. And as a result, F naught 2 equals to 400 hertz. That simply means we've done all this solving just to realize that my answer is the same as my question. Who said JAMB do not have sense of humor? So our answer and our question are the same. The variation in the tension and in the length ended up cancelling each other out. Now this solving may look a little bit long and difficult, but I'll just remind you that this is again from the year 1994, and older JAMB questions, they had more time, so the questions were a little bit more difficult, but also as long as you know what you are doing, you can finish solving this in less than a minute. It's not that long. Okay. Our next question from the year 1995, question 24. 1995, question 24. The pitch of an acoustic device can be increased by, obviously, we when we learned our theory, we said the one thing that affects pitch is what? Frequency. That means option B is definitely wrong. The amplitude doesn't matter to the pitch. Option C is also wrong. The loudness doesn't matter to the pitch. Option D also is wrong. The intensity doesn't matter to the pitch. The only thing that affects the pitch is that this pitch can be increased by increasing the frequency, and that is option A. You see, these are very, very, very simple. Okay, for our next question, we are moving on. We are moving on. This is 1997 right now. The year is 1997. And we are looking at question 24. This one says, under constant tension and constant mass per unit length. Constant tension and constant mass per unit length. The note produced by a plucked string is 500 Hz. When the length is 0.9 meters. At what length? So, because I'm comparing two different scenarios, F1, L1, at what length, L2, is the frequency F2 150 Hz? At what length does this happen to the frequency? Now, I've been told that the tension and the mass per unit length are to be kept constant, which means that the only thing left in my formula to change is that F naught equals to 1 over 2L. This is it remaining. Everything is now constant. And since node 2 is just a number, it too is constant. And therefore, K equals to F naught L. You see, you have to be able to create all these formulas at times for easy solving. Because now we know that F1, L1, which is F times L, equals to F2, L2. I want to find L2, so I now divide both sides by F2. And therefore, L2 must be F1, which I know is 500, times L1, which I know is 0.9, divided by F2, which I know is 150. So now we have to simply open our calculators, which you can do on your JAMB app. I'm doing that here with my phone, and see 500 times 0.9 divided by 150. And that gives you 3 meters. Now I go back to my JAMB app and realize, yes, that is option A. So you see, whenever you are given a question to compare two things, what you simply have to do is cancel out those things that are not changing in the formula. Those things that are not constant, we made them K, and then we'll solve the relationship between the ones that were actually changing. And from that, we could create our new formula, shorter version of the formula at least, to solve this particular question. Okay, now on our three schools JAMB app still, let's find our next question. This one is from the year 1998, yes, 1998. Question 2. This one says, the velocity of a sound wave at 27 degrees Celsius, just wipe this part of the board. The velocity of a sound wave at 27 degrees Celsius is 360 meters per second. Then its velocity at 127 degrees Celsius is what? So I want to find this new velocity. How do I go about that? Remember, we have a formula for this, but I was specific that your temperature must be in Kelvin, not Celsius. And converting from Kelvin to Celsius, you simply have to add 273. which I've done, and now I know my temperature for both in Celsius, or rather in Kelvin. Therefore, my formula was V2 over V1 was to the square root of T2 over T1. My V2 is unknown, but my V1 is 360 equals my T2 is 400, my T1 is 300. So these zeros can cancel out. V2 must be equals to 360 after cross multiplying times square root of 4 over 3. Now if I look at my options, I can see that my options are all in surd form, not decimal. That means I don't have to use my calculator to find square root of anything. I have to simplify this as best I can. How do I do that? Well, what's the square root of 4? 2 over root 3. That's 720 over root 3. But as we are aware, in mathematics, we don't leave a surd form as denominator. We rationalize. And how do we do so? By multiplying by root 3 over root 3. That will give 720 root 3 over root 3 times root 3 is 3. 3 into 3, 1. 3 into 7 here is 2, remember 1. 3 into 12 is 4, and that's 0. That means I'll be getting 240 root 3 meters per second. When I open my Auto Schools JAMB app, I can find that that is my option C. So you see, these are pretty simple. We've solved several already. So for our fifth question, but actually this is theoretical again, so don't bother writing it. The physical properties of sound can best be described by. Now I'm going to give you the options in a scattered manner, just so that we can try to analyze and try and get to the answer. We'll start with option D. Option D says polarization and refraction. All waves can be refracted, but you must remember only transverse waves can be polarized, and sound is a longitudinal wave, not a transverse wave. Therefore, polarization is not one of its properties. As such, it cannot be D. Option C says polarization and diffraction. Yet again, polarization cannot be included, so no. Option B says polarization and reflection. Again, we insist polarization cannot be one of the properties of sound wave. And that means our answer must be A, which is reflection and diffraction. That is common to every single wave, and sound is no exception. Okay, the next question says, in a closed organ pipe, producing a musical note, an antinode will always be produced at. And I explained this while we are doing our analysis. I said you can differentiate between your different types of pipes by the position of the nodes and the antinode. In a string, I'll repeat this one more time for emphasis. In a string, the nodes are always at both ends. Both ends carry nodes. In an open pipe, both ends carry antinodes. In a closed pipe, the closed part carries a node, and the open pipe carries an antinode. The open part carries an antinode, while the closed part carries a node. Therefore, this question is asking us, where will the antinode be? And obviously, the antinode will always be at the open part, which in this case is the open end. See, very simple. Just do not forget those keywords. Okay, and that leads us to our next question, which is from the year 1998. 1998, number 25. This is our fourth solving, but I believe this should be our seventh or eighth question overall. This one says, a steel wire of length 0.5 meters, length is 0.5 meters, is stretched between two fixed points, and its fundamental frequency is 200 hertz. The speed of the wave is what? This is simple. We know we are dealing with a string and we know how strings work. Now we are told we are dealing with fundamental frequency. Fundamental frequency means it must be like this. Sorry. This. And as such, lambda equals to 2L because L equals to lambda over 2. And as such, can I get my wavelength? Yes. 2 times 0.5, and that is 1 meter. And as such, V equals to F naught lambda, which is 200 times 1, which is 200 meters per second. That is option C. So you see, once you remember all the terms you are dealing with, the parameters, the behavior you're solving is very, very simple. Okay, we are going to remain at that here and actually just move one question down. Still at 1998. From 25 now, we are going to question 26 for our fifth solving in this topic. And it says, in a resonance tube experiment, if the fundamental frequency of the vibrating air column is 280 Hz, then we have to find the frequency of the third overtone. Now, quite simply, the third overtone is your F3. Very easy. So, first question we have to ask ourselves is which type of pipe is this? Now, please note, a resonance tube experiment is always done with a closed pipe. It's that simple. You have to note that resonance tube experiment simply automatically equals closed pipe. And as such, if I'm dealing with a closed pipe, the formula is Fn equals to 2n plus 1 F naught. Therefore, F3 must be 2 times 3 plus 1, and F naught is 280. So 2 times 3 is 6 plus 1 times 280. 6 plus 1 is 7 times 280. And if I use my calculator, 7 times 280 is 1960 Hz. Which, when I go back to my O3 Schools JAMB app, is definitely option D. So you see, the solving is quite simple. Okay, we move on, and now we'll go to the year 1999. Question 18 for the year 1999. This is our number 6 solving. The lowest note emitted by a stretched string has a frequency of 40 Hz. The lowest note is always your fundamental frequency. The question is, how many overtones are there between 40 Hz and 180 Hz? So this is a string. Want to know how many overtones there are between 40 and 180. This is fundamental. To get this is very simple. You can simply say your first overtone F1 will be 2F notes, which will be 2 times 40, 80. It falls between. Your second overtone, 3F notes. Okay, that becomes 3 times 40, which is 120 Hz. Your third overtone, that's your 4F notes. It's going to be 4 times 40, 160 Hz within the limit. Then your fourth overtone, which is 5F notes, going to be 5 times 40, 200 Hz, which is over the limit. Therefore, the overtones are here within 40 to 180 are the first overtone, the second overtone, and the third overtone. And that is 3 overtones. Option B. See? Very simple. Next up, let's look at the year 2000. Question 18. 2000. Question number 18. A sonometer wire, which as we are aware is used to test for the frequency of sound. Sonometer wire is vibrating at frequency F naught. If the tension in the wire is doubled, while the length and the mass per unit length are kept constant, the new frequency of vibration is what? So basically, the length and mass per unit length are not changing. All that is changing is the tension. And as we know in the sonometer wire, the frequency is proportional to the square root of the tension. In case you are not sure of this, remember your formula 1 over 2L square root of T over M. Constant, constant. So you have just square root of T remaining. And as such, K must be F naught over square root of T. Therefore, my initial frequency of vibration, F naught, divided by the initial tension, T, equals to the new tension, let me call that F10 for the square root here, then square root of, what happened to the tension? Tension is doubled, so this should be 2 times T. Okay, let's make Fn square root of formula. That becomes F naught times this root 2 is going over there. That's 2T over T. And T can cancel T. I'll be left with F naught times root 2, which obviously is same thing as F naught root 2, which is option D. So as you can see, all these solvings, no matter how they look or how intricate it may appear, they are all very simple once you know your formulas. That leads us to yet another question in the year 2000, but this time question 24. Now for this one, we are told a transverse wave is applied to a string whose mass per unit length, remember, mass per unit length is calculated at M, is 3 times 10 to the power minus 2 kilogram per meters. If the string is under tension of 12 Newton, we have to find the speed of propagation of the wave. Now we already know that velocity in this situation must be square root of T over M. So it's quite straightforward. So we put in your values. Square root of 12 divided by 3 times 10 is power minus 2. Do this one separate. 12 over 3 is 4. Now, this 10 power minus 2 is going to come up. And from the laws of indices, as it goes up, the minus leaves. That becomes 10 raised to power 2. 4 times 10 raised to power 2 is 400. And the square root of 400 is 20. So we have 20 meters per second. See? Almost done. Let's take just 2 more, I believe. And we shall call it quits with our calculations on that sound waves. That leads us to question 9. It says a plane sound wave of frequency 85.5 hertz and velocity 342 meters per second is reflected from a vertical wall. At what distance from the wall does the wave have an antinode? Tricky, right? At what distance from the wall does this wave have an antinode? Well, before we can talk about the nodes or the antinode and where they will be located, let's first off start by finding the wavelength of this wave. So we can see V equals to F lambda, and as such, lambda must be V over F. So 342 over 85.5 will simply give us 4 meters. So the wavelength of this wave is 4 meters. Now let's try and draw this wave, shall we? Even if we assume this wave is simply something like this. Now, what do we know about this wave? We know since the aspect about antinode, you know here must be a node, antinode, node, antinode, node. Even if that's it. Now the wavelength is 4 meters. That means here is node. This next node is at half of the wave, and this first antinode occurs at a quarter of the wave. So where is the antinode? Quarter from the wall. That means 1 over 4 times 4 meters. 4 cancels 4. That is simply 1 meters. So my first antinode appears 1 meters away from the wall. Very, very easy. And now we can take one last question. And this time from the year 2001, question 12. This one says, a string is fastened tightly between two walls 24 centimeters apart. 24 cm apart. The wavelength of the second overtone is what? The wavelength of the second overtone is what? Now, if now we're dealing with the second overtone, it means we've done the fundamental frequency, then the first overtone, and then the second overtone. Now, we know fundamentally it should be like this. Even if you cannot think about it initially, you can try and go stage by stage. This is fundamental. After this, my first overtone must be this. And as such, my second overtone must be this. You see? So my length is still 24 centimeters. So what should the wavelength now be in this situation? How many wavelengths do I have here? Half a wavelength, another half, another half. That's 3 halves, which is 3 over 2. That means my length equals to 3 over 2 wavelengths. That wavelength must be 2L over 3. So that becomes 2 times 24 over 3. And that is 2 times 24 is 48. 48 over 3 is 16 centimeters. And therefore, the wavelength of this wave becomes 16 centimeters. And with that, we've come to an end of this class on sound waves. There are many more questions on this topic available to you in your O3 Schools JAMB app. Please do well, go there and solve as many as you can. The formulas, the methods are all this same method. And okay, with that, I want to thank you very much for watching this class. Do subscribe to this channel to gain access to videos on different courses and subjects, different topics even within the subjects, all presented to you courtesy O3 Schools JAMB app. Remember, download your app and simply activate your app to enjoy full functionality. Thank you again for watching. My name is Athanasius.